I'm not sure if these are in any particular order relative to the chapters, but be that as it may, we'll start with number 1. So elements in group, we're going to refer to the periodic table. Elements in group 1A and 7A. This is the old system. The new system, remember, goes from left to right, 1 through 18. The old system has some advantages. It works through the first 2 groups on the left, alkaline metals and alkaline earths. And then skips over the transition metals and works on the last 6 columns. So what it also tells you is that the Roman numeral is the number of valence electrons. So the answer is 1 and 7. Where is it? Here it is, 1 and 7. Okay. That's one of the advantages of the old system. Let's see. 2. I'm going to scroll anyway. So I think we've got several in a row. Yep. 2. Formation of a positive ion. So what's required to form an ion? You either have to lose or gain electrons, right? So if you form a positive ion, the temptation is to add positives. Right? You can't do that with an atom. Because if you add positives, that means you're adding protons. And that means you're changing the element. So everything happens with gain and loss of negatives, electrons. So in order to get a positive ion, you have to lose a negative. It has to lose an electron, at least one. And that'll give you an imbalance toward the positive side. So let's see, the answer to that one is you got to lose 1 or more electrons to make a positive ion. Okay. How many total electrons are present in N3- ion? Total electrons. Let's see, let me identify that for the viewing audience. Okay. If you need total electrons, look to nitrogen on your periodic table. What's its atomic number? 7. Okay. So it's got 7 electrons to start with, but we've got an extra 3 added on top of it. So that's 10 electrons, right? Okay. This is kind of elementary for you. A little bit of review probably wouldn't hurt. Okay, so elements in group 2A and 7A would be expected to form ions with charges of what? Now you have to look at where they're located, what kind of elements they are. The 2A's have 2 valence electrons. And if we're going to obey the octet rule, let's see, we're on 4. For 2A's, you've got 2 valence electrons. For 7A's, is that the right one? Yeah, 7A's. You've got 7 valence electrons. So you have to ask yourself, what's the best way, the easiest way, the lowest energy way to make an octet? With these, you make an octet by adding an electron. But with these, you make an octet by subtracting 2 electrons and backing up to the next noble gas. Okay, so let's go back to the question. With charges up. Okay, so if we're going to subtract 2 electrons to get to the noble gas form, that means we have an imbalance of 2 positives. And we take 2 negatives away. Okay, when we add 1 electron, now we're adding an imbalance of 1-. So the answer would be a 2 plus and a 1 minus. Let's see, here it is, 2 plus and 1 minus. Okay. Alrighty. 4, 5. I think I need a new marker. The correct formula for the ionic compound that might be formed from sodium and arsenic. Okay, where's sodium? It's in the first group, right? Right, alkali metal, so it has only one possible charge, right? +1. And arsenic is in what group? It's in the nitrogens. It's below nitrogen. Right, so that means it prefers -3, right? Halogens -1, chalcogens -2, nitrogens -3. So we just need 3 of these to balance that -3. So Na3As should be our answer. Okay. Six. We will begin skipping a few down the line. In which of the following pairs of compounds are both members of the pairs ionic? Okay, if they are ionic, they're going to have a metal non-metal relationship. So we need a metal with a non-metal. So we can, by process of elimination, we can say both members of the pair are ionic. So phosphorus and iodine are both nonmetals, so A's out. Hydrogen and sulfide, hydrogen is kind of a special case. But we can say that nitrogen and chlorine are both nonmetals, so they're out. How about lithium and fluorine? Now that's ionic. Lithium's a metal, fluorine's a halogen, non-metal, but water's not. Right? So by process of elimination, this one should be the right one. Lithium and iodine, definitely ionic. Nickel and oxygen, that's definitely ionic also. So the answer to that one is D. Okay. 7 at the bottom of the page. Let me scroll that one. I bet there's some more behind it. There we go. The correct name for the ionic compound, Fe2Se3. Okay, first of all, what elements do we have? Iron, Selenium, Okay, metal, non-metal. So it's either a type 1 or a type 2. How do we tell the difference between type 1s and 2s? We look to the metal. Can it have more than one possible charge? Yeah, iron can. Okay. So it's a type 2. So the rules for type 2 is you have to say what the charge is. That means we have to deduce from this, what is the charge of iron? So we look at selenium for the negative. And selenium is in the chalcogen group with oxygen. That means it has a -2 charge. So -2 times 3 is -6, right? -6. That means these two irons have to generate a +6 to balance that charge. But there are only 2 of them. So each one of them has to be a +3. Now, that's how we say the charge on iron. Iron 3, actually, we're not finished yet. Change the ending to IDE. So iron 3 selenide should be the correct answer. Another quick way is this is kind of an assumption. Assume when you were writing the compound originally, or whoever was writing it, found that the easiest way to deduce the subscripts was to cross multiply. So they brought the 2 over from here and the 3 over from there. So if I were naming on the fly, I would see that compound and I would say, oh, iron 3. Iron 3 selenide. But this is how we deduce it longhand. Okay, 8. Which of the following statements about polyatomic ions is correct? Okay, polyatomic ion, let's characterize it. Poly, well, it's got lots of atoms, right? Poly means many, so it's got many atoms, but they have a special relationship. They form an ion, but since they're polyatomic, the charge on the ion is spread over the entire group. Nobody has claim on the charge. Not an individual atom does not have claim on the charge. They have to be together, locked in such a way that they behave as a single unit. Okay, so with that in mind, let's see which one of these fits. All have the names with the ending ATE. All you have to do is think of one exception, and all is false. Right? Think of my favorite is the chlorines and the oxygens together. ClO3 minus is chlorate. ClO2 minus is chlorite. Okay, so we know this one's out. All must contain one of the halogens. Is that true? I can think of one right off the top of my head. Hydroxide. No halogens in that one. Okay, so that one's out. All negative ions are more common than positive ions. Oh, A, that means answer. Negative ions are more common than positive ions. Yeah, that's true. In fact, in our list, we only had one positive. Remember which one it was? Stretch your brain a little bit there. It's got nitrogen in it. It's got hydrogen in it too. How many hydrogens? 4. Ammonium. Okay. That's the only positive one that was in our list. There are some other positive ones, but they're kind of obscure. Okay, so this one is right. All carry a charge of 2. Nah, they're all over the board. Okay. Number 9. The formulas of the sulfate ion, the nitrate ion, and the phosphate ion are respectively. Okay, so you just have to, in this case, since I'm giving you the polyatomic chart, you just look them up. Right? You could remember them if you use them enough. Yeah. So sulfate there. Nitrate and phosphate. There you go. So that would be this one right here. So just for kicks, if we were going to make an acid out of each one of these, the hydrogen is going to have a positive charge, one positive charge. So this one would need 2. This one would need 1. That would need 3. And then you just have to put them in solution. And you'd have an acid. All right. That's good. Picks up 10 and 11. Okay. In which of the following pairs of ions are the 2 members of the pair isoelectronic? Okay. Remember what we mean by isoelectronic. It doesn't mean that they have the same number of electrons necessarily. That's one of the conditions. But they have the same electronic structure. That's isoelectronic. So in order to be isoelectronic, what's the quickest way to get to the answer? Look at, yeah. Well, yeah.
I don't know what I'm trying. Yeah, I don't know what I'm trying to say.
Yeah. Look at their charges. Right. Each one of these has a charge. Are these their characteristic charges? Right. That's a halogen. Yep, that's right. That's a chalcogen. That's right. That's an alkali metal. That's an alkali metal. Those are right. Aluminum is always 3+. That's a pnictogen. And when it's an ion, it's a 3-. Okay. Now, ask yourself, if these are characteristic charges, why are they characteristic charges? Because they're trying to look like a noble gas. Okay. So sulfur with 2 minuses is going to look like argon. Okay. How about chlorine? Chlorine's got a minus. It's trying to look like argon too. So that one is isoelectronic. With those charges, they both look like argon. Okay, how about sodium and potassium? Well, sodium, losing 1 electron, it goes backwards. So it looks like neon. Potassium loses 1. It goes backward, but it looks like argon. Right? So that one can't be. Okay. How about aluminum? Aluminum 3+. Aluminum loses 3 electrons, so you go backwards, right? Aluminum, magnesium, sodium, neon. So aluminum is going to look like neon. Aluminum 3+. How about nitrogen 3-? You add 3 minuses to it, 3 electrons. Nitrogen goes nitrogen, oxygen, fluorine, neon. So this one looks like, these both look like the same noble gas. So you have more than one correct response. Okay? You thought we were going to have to sit down and draw out the electronic configurations, didn't you? Even chemists like to take the easy route. 11. Now you may want to ask yourself, could I draw the electronic configuration? Well, yeah. Sulfur. You could use the shortened version. Sulfur looks like neon plus sodium, magnesium, aluminum, silicon, phosphorus, and then sulfur. So you just add those two. That's the shorthand version. Okay, 11. Which of the following elements would be expected to form a monatomic ion with a charge of +2? So we need a monatomic with a 2+ charge. Oxygen. Now that's a 2-. Sulfur. That's a 2-. Magnesium. That's an alkaline earth. All of those are 2+. So there's only one response. Magnesium. I guess what we're doing here is also testing your ability to navigate the periodic table and to use information that it gives you. And it gives you a lot of information. Okay, oops. Scroll. There we go. 14. Which of the following pairings of compound name and compound formula is incorrect? Okay, so they have to behave. Incorrect. Okay. How about sodium oxide? Is that correct? Sodium's a fixed charge, it's the metal, right? So sodium oxide would be a correct name. You only have to say sodium and oxide. But is the formula correct? Well, yeah, oxygen's -2, sodium's +1. So you need 2 sodiums. All right, so A is correct. Magnesium sulfide. Magnesium prefers a 2+ charge, right? Sulfur prefers a 2- charge. And the metal is a fixed charge. So it's type 1. So we'd say magnesium sulfide. The name is correct, but the formula is wrong because you don't need a 2. It's just MgS. 2+, 2-. The balance with a 1-to-1 ratio. Right, so that was false. That was correct. That was correct. Well, we found our answer. Oh, more than one correct response. Okay, so we got to check this one out. Potassium chloride. Uh-oh. Potassium chloride. That was correct. Right? So D should be the answer, not B. Wait a minute. Incorrect. I'm sorry. Incorrect. Okay. I read my own questions. Okay, so we found our answer. 15. Which of the following compounds contain more than 10 atoms per formula unit? More than 10 atoms. Okay, so we got to write the compounds. Right? Ammonium phosphate. That's a plus, this is a 3-, right? Okay, so that means we need 3 of those polyatomics to balance the 3- on that polyatomic. Well, let's see, this has got 3 + 12 is 15, we're already over 10. So this one is more than 10. Aluminum carbonate. Right? So that's a polyatomic. If you don't remember the charge, just look it up. 2-, 3+, right? Okay. So here's a case where cross multiply works pretty well. 3 over here, 2 over there. So we have 2 + 3 is 5, + 9 is 14. There's another one. That's more than 10. Iron 3 cyanide. Cyanide is -1. So we need 3 of them, right? So that's 3, 6, 7. Nope, that one's not more. But we do have more than one correct answer. Okay? All right, let's page and see. Oops. Here we go. Stop on that one. Okay. You've seen these before. Nobody likes these. So We look at each one of these statements and see, is it true or false? And then the answers down here, all three are true. Two of the three are true. Only one is true. None are true. Okay, so we have to look at each one. The ions O2 minus and S2 minus are isoelectronic. Using our noble gas trick as before, oxygen plus 2 electrons makes it look like neon. I'm looking at the periodic table. Sulfur with 2 ions makes it look like argon. So that one's false. Right? They're not isoelectronic. The symbol for an atom of X that has lost 2 electrons is 2 minus. Sorry. You lose 2 electrons, you're favoring the positives. Right? So that one's false. In all ionic compounds, the total charge of the ions present per formula unit must add up to 0. Bingo. Right? Only one of the statements is true. All right, let's scroll to 20. Okay. Same scenario as 19. Calcium sulfide is a compound in which both types of ions present have the same electronic configuration, that of the noble gas argon. Let's see, calcium would be 2 plus, sulfur would be 2 minus. Let's see, calcium would lose 2 electrons and look like argon. Okay, sulfur would gain 2 electrons and look like argon. That's true. This statement is check. The charge on the positive ions present in the compound aluminum sulfide is +3. The positive ion. Which one's positive? The metal. And it does have a +3 charge. That one's true. The polyatomic ions, ammonium and cyanide, do not contain oxygen. Right? Ammonium and cyanide. That's true. So all 3 of those are true. Let's see, 21. We could do 21, but let's scroll it up so we can see it better. We'll pick up 22. 21 and 22. All right. Okay. For the electronic configuration, 1s2, 2s2, 2p6, 3s2, and 3p5, choose the appropriate number of valence electrons from this response list. How do we know the valence electrons? They all have the same principal quantum number. They're all at the same energy level. That means we have 2 plus 5 is 7. 7 valence electrons in this configuration. Okay? (22). For this electronic configuration, let's see, does it look kosher? 4s, 3d, 3, okay. Looks good to me. Remember, when we get down to 4, we start to cross over the transitions, and they back up to the Ds. They back up to the 3Ds. And then once we get past them, we get to the 4s again in that period. Choose the appropriate number of valence electrons present for the response. Well, it'd be 3 plus 2 is 5. These are at the highest energy level. Now, that seems counterintuitive or counter to what we've learned about the energy distribution of electrons, right? Because this is low, next high, high, next high, next high, next high, next high. You say, wait a minute, that was higher energy than this one. But by definition, the valence electrons have the highest principal quantum number. What would that be, by the way? 4. 1, 2, 3, 4 would be potassium, calcium, scandium across to zinc, and gallium, germanium, that's arsenic. You can tell that just by looking at the configuration and reading your table. Okay, let me scroll that one so we can pick up. Just pick up 2 of them. See if I can do this. 25 off screen, so when I page it, it'll come up right. 23. For the ion or element combination of M2 plus and X minus, this would be the metal, that would be the non-metal. Choose the correct formula for the compound. You just have to balance the charges, right? So it'd be MX2. Because you need 2 minuses to balance that 2 plus. (24) Choose the correct formula of the compound formed when M is in group 3A element and X, which is in group 6A, are combined. Okay. Now you have to work a little harder. So if M is in group 3A, it's going to have a 3 plus charge, right? Because there's 3. It's either boron, aluminum, gallium, indium. One of those has a 3 plus charge. And X is in 6A. 6A is the chalcogens. So it'll have a 2 minus charge. So that formula would be 2x3. Just 3 over here, 2 over there. And you can check yourself. Minus 2 times 3 is minus 6. Plus 3 times 2 is plus 6. They balance. And in this case, that's D is the answer. Let's see. 25 and 26 anyway. Choose a formula from the response list where a greater number of negative ions are present than positive ions. A greater number of negative ions. Well, this is fairly simple. You just have to realize how we write compounds. Positive ions first, negative second. So you look at the negative seconds and you say, greater number of negative ions than positive. Can't be this one. That's 1 and that's 3. There's 3 and there's 1. That's good. This is 1 negative ion, and that's 1 positive ion, so they're equal. This one's 2 positives and 1 negative. So B is the only possibility here. (26) Choose the polyatomic ion that contains a total of 4 atoms. Okay, hydroxide. Nope, only 2. Ammonium, NH4 plus, nope, that's 5. 5 atoms. Nitrate, NO3 minus, there you go. That's 4. Sulfate is 5. So nitrate answers that question. 26. Let's see, 27. I need to scroll that one. Pick up the 2 in this one. Yep, here we go. 27. Choose the polyatomic ion that contains 1 hydrogen atom. Well, let's see. OH minus one hydrogen. NH4. Oh, four hydrogens. NO3 minus no hydrogens. Okay. Sulfate, no hydrogens. So hydroxide has to be it. That was 27. 29. Okay. Which of the following molecular compounds would have a Lewis structure that contains 10 electron dots? Okay. So we have to draw the structure for each one. Remember how to do that for this one? How many valence electrons do we have? 1 plus 4 is 5. Plus 5 is 10, right? That's it. 10 electrons. And you got to place those 10 electrons in the structure. The Lewis structure contains the total number of valence electrons. So we found our answer actually. 10 valence electrons means 10 electron dots. This one would be, let's see, oxygen is 6 plus 2 is 8. This one would be 3 plus 5 is 8. This one would be 4 plus 6, 12, 16 for carbon dioxide. So that's all you have to do. And in fact, you don't have to draw the structure. You just have to count the valence electrons. Okay. Yeah, it was there. 30. I don't know why I have all that space. Oh, it's a page break. Total number of non-bonding electron pairs present in the Lewis structure of SiH4. Non-bonding pairs. Okay. So we will have to draw this structure. Silicon. It's in carbons group, so it has 4. And that's 1 for each hydrogen is another 4. So we have 8 electrons. Silicon in the middle. 1, 2, 3, 4. 2, 4, 6, 8. We used them all up. There are no non-bonding pairs. 0. Sometimes called lone pairs. Okay, 31. In which of the following molecules is a coordinate covalent bond present? Okay. One of the things that I said in my lectures was once the compound is formed, they all look alike. In other words, you can't tell where they came from. So this is sort of a detective story. You deduce which one is most likely to be coordinate. So that means both electrons from the bonding pair are donated by one atom. They don't have one from each shared. So I would look at each one of these and say, okay, if we've got a coordinate covalent bond somewhere, then look at their structures and say, which atom could you remove and still have a stable molecule? Okay, because the stable molecule is happy the way it is, except when it bonds with this new atom, it's got to donate 2 of its electrons. Right? So let's look through these and see which one would be a stable molecule. If we removed nitrogen, I don't know any compound that has just 1 hydrogen and 1 carbon, right? So that one. Or remove the hydrogen, then you get the cyanide ion, Cn minus. How about this one, carbon dioxide? Well, we can't very well remove one of the oxygens without making a CO. What does that look like? Dinitrogen? No, that definitely shares, right? It shares 3 from this one and 3 from that one. This one's the most likely one. It looked like that until oxygen came along. And then dinitrogen monoxide, laughing gas, formed. Because it took, this one has 2 lone pairs, like that. And this oxygen comes in, it needs 2 electrons to look like neon, right? And it gets those 2 electrons from this nitrogen to form that bond. So it's kind of a best guess situation. Okay, 35. Coordinate covalent bonds differ from normal covalent bonds. Should have done this one first because this is just definition. One atom supplies more electrons to the bond than the other atom. Actually, up to this point, we've only defined coordinate covalent bonds as one atom donates all the electrons for the bond. But is that the best answer? The electrons of the bond move about in a coordinated path. I don't know. I was searching around for a filler answer. Atoms involved must always also possess non-bonding electron pairs. Not necessarily. I mean, sometimes they do. More than one correct response. Now, since B and C are ludicrous, A is the only possibility. Well, you could say no correct response. Let's see, would that be correct? I mean, would that be valid? One atom supplies more electrons to the bond than the other. If we're going to pick the best answer, A would be better than E. Because A sort of has a kernel of truth in it. That's a difficult question. I can see where that might confuse. Must have been made by a career chemist. Not like me, like a backdoor chemist. Okay. Let's scroll and get both of those. 37. Which of the following statements concerning molecular polarity is correct? Okay. How do we know polarity of a molecule? Well, first, you have to draw the Lewis structure. Then you have to decide, are the bonds polar? Then you've got to look at the geometry. Do those polar bonds cancel one another out? Or is there a net dipole for that molecule? Okay, so of these answers, let's see which one satisfies. All diatomic molecules are polar. No, not all of them. Right? Some of them are non-polar. Diatomic, that's definitely non-polar. So all you have to do when it says all you need is one exception, and that invalidates them. So all diatomic molecules are polar is false. How about B? All linear triatomic molecules are nonpolar. Linear triatomic. Can you think of an example where, well, let's see. How about this one? Okay. This one has no lone pairs. 2, 4, 6, 8. Carbon's satisfied. That one has a lone pair. But this would be linear, right? It's got 2 groups. According to the VSEPR model, 2 groups means linear. So that was linear. But nitrogen is more electronegative than carbon. And carbon is more electronegative than hydrogen. So that one's polar, right? We've invalidated this with that one molecule. All linear triatomics are nonpolar? No. We have examples of polar linears. How about triatomic, let's see, triatomic molecules in which all bonds are polar must be polar. How about this one? Boron trihydride. That's all of it, right? Boron's got 3 valence electrons, and it's got 1 from each of these, makes 3 bonds. There are no extras. So 3 bonds, three groups around that central atom means trigonal planar, which means it's nonpolar. But boron is more polar than hydrogen. So all those bonds are slightly polar, but the overall molecule is nonpolar. So all the bonds are polar, but the molecule is not polar. So we've got an example here that invalidates this one. So that means none of these are correct. How about 38? For which of the following pairs of compounds do both members of the pair have names that contain the prefix di? Okay, why would we put di as a prefix in a name? Has to be a type 3 compound, right? It's not ionic. They're both nonmetals, and we just have to say how many there are. So I would look for the first condition. I'd look for if both members have names that have prefix di. First, I'd look for both of them are nonmetal, nonmetal. So nonmetal, nonmetal, metal, nonmetal. Can't do that one. How about this one? Nonmetal, 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 nonmetal. Could be. 2 nonmetals could be. Okay. Both members of the pair have names that contain di. Okay. Carbon dioxide. Yep. Dinitrogen monoxide. Right. Nitrous oxide. Old-fashioned way. That was true. How about this one? Dinitrogen trioxide. Yep. This is kind of tricky. We typically name this one hydrogen sulfide. We don't say di. But if you strictly adhere to the rules, it would be dihydrogen sulfide. Right? So that's a bad question. Right? Instead of saying this one, you could say more than one correct response. Unless we're going to say that this one behaves like a metal nonmetal. It depends on the difference in their electronegativities. Is the difference between sulfur and hydrogen great enough to ionize that bond, to ionize hydrogen? I don't think so. So this one is actually, should be D. Let me mark that one for further inspection. 238. Yeah. Let me check this one. All right. 38. 40. Oh boy. All right, let's see which ones of these 3 are true. Once a coordinate covalent bond is formed, there's no way to distinguish it from any of the other covalent bonds in a molecule. That's true. They all behave alike. A covalent bond is a covalent bond is a covalent bond. The least electronegative elements, that's true. The least electronegative elements are located to the far right in the periodic table. Now it's the other way around. The more electronegative they are, the further to the right they are. The most electronegative one in the periodic table is fluorine, upper right-hand corner. The least electronegative is cesium in the lower left-hand corner. So that was false. The central concept of VSEPR theory is that the electron groups in the valence shell of a central atom in a molecule attract each other. You try to position those groups so that you minimize repulsion. They repel each other because they're made of electrons. That's the central concept of VSEPR. Not that they attract, but that they repel. So there's only one answer here. Only one statement is true. All right. Let's see. 44. Stayed on the screen. Let's see how many of these three are true. An unpaired electron is present in the Lewis structure for the molecule NO. Okay, so we have to draw the structure for NO. How many valence in nitrogen? Looks like 5. Valence in oxygen? 6. So we have 11 valence electrons that we have to position. Right? There's 2 of them. That's 9 electrons. Now we start positioning around. So 1, 2, 3, 4, 5, 6, 7, 8. Doesn't matter which side, 9. Okay, so we've got 1, 2, 3, 4, 5, 6, 7. Or we've got 2, 4, 6. Oxygen needs 2 more. So how are we going to do that? We have to take a pair of electrons from here and make a bond. If we take it from here, that doesn't help oxygen at all. Then it's got 2, 4, 5, 6. So we have to take 2 of these, right, and make a double bond. Still got these. And now we've got these 2 and that one. So that leaves 2, 4, 6, 8. 2, 4, 6, 7. Nitrogen is deficient by 1 electron. Okay, let's go back. An unpaired electron is present in the Lewis structure of the molecule. Well, yeah. In fact, there's more. Well, okay. These would typically be written as paired. Okay, but we still have this unpaired electron on nitrogen. So that's true. 1 is true. The molecule nitric oxide is naturally present in the human body. Yeah, that's true. You don't even have to learn chemistry to know that one. Just listen to the commercials. What is it? Super Beets, right? You have to mix up a drink with a beet powder, and they say it's pretty nasty. Now they've got them in gummies and they've got them in pills you can swallow, and you can get the Super Beets, and it's supposed to boost your nitric oxide. Nitric oxide, they found, will dilate vessels. So it has an effect on the smooth muscles that surround the blood vessels, causes them to relax. And that decreases your blood pressure, increases blood flow. I'll buy it. I'll buy the concept. I won't buy the product yet. Maybe I should, because my blood pressure is kind of borderline. Anyway, let's see. I must have accidentally hit a button. So this one's true. The acronym ORP stands for odor replication process. No, I don't think so. What does it stand for? ORP. I bet that came out of your textbook because I didn't introduce it in class. You'd have to look that one up to find out what it is. But this is obviously not the right answer. So 2 of the above are true. You're going to find out what it is?
I'm trying to look it up.
Okay. I'm curious. What does it really mean? At one time, I probably knew, but I don't remember now.
Oxidation reduction potential.
Close enough? Yeah, that sounds reasonable.
Sounds like chemistry to me.
Yeah, that's chemistry. Okay, 45. Choose the correct number of shared electrons in the Lewis structure of H2O. All right, if you remember H2O, right, it's like that. The hydrogens can only have a single bond. Oxygen has a couple of unused lone pairs. So you have, what does it say? Correct number of shared electrons. Correct number of electrons. 2, 4. 4 shared electrons. 46. Characterize the bond that forms between carbon and hydrogen. Okay, what are these numbers? Those are electronegativities. Okay, electronegativities. So what's the difference between them? If you need to characterize the bond, you subtract the smallest one from the larger one, and we get a value of 0.4. So I don't have that chart with me, but 0.4 should be covalent and nonpolar. Nonpolar covalent. If you get above 0.4, between 0.4 and I think 1.2, you have polar covalent. And then above 1.2, you have ionic if it's a metal nonmetal. And if they're both nonmetals, then you still have polar covalent. You have to, it's sort of a gray area. But we don't need the gray area to answer this one. 0.4 is the difference. That makes it covalent and nonpolar. Okay. 47. We do have some diagrams, but you don't have to draw any yourself. Unless you need to do like we're doing to deduce the answer. But you don't have to present drawings as answers to questions. Characterize the bonds that form between lithium and oxygen. So that would be 3.5 minus 1.0, which is 2.5. That's definitely ionic. Actually, we wouldn't need these values, right? They're far enough apart. Lithium's way over on the left, oxygen's way over on the right. You know it's going to be ionic. But quantitatively speaking, we can prove it. 49, I better scroll that. There we go. Compound with a trigonal pyramidal geometry. Trigonal pyramid. Okay. What they're saying here is that the geometry of the molecule, the molecular geometry, not the electronic. So the molecular geometry, first you would deduce the electronic geometry, and then you would sort of cover up the lone pairs and say what's left over. Well, for this, water, with these lone pairs, the electronic geometry is going to be tetrahedral. But if you cover up those lone pairs, it's going to be bent as a molecular geometry. Right? So it's not trigonal pyramid. How about this one? And you have to also assume that they're talking about the central atom. Geometry relative to the central atom. Here, 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 here. Okay, so this one's going to be, it's only got 2 groups around that nitrogen. That's linear. It's linear electronic. It's linear molecular also. Right, so that one's not here. This one has 1, 2, 3, 4 groups. So it's tetrahedral. And then you cover this one up. And what do you have left? Well, if you have tetrahedral, like that, and you have your phosphorus in the middle, then you have your hydrogens here, here, here. The bonds, the actual bonds are between this one, and this one. So when you cover that up, you have a trigonal pyramid. Okay, that's the answer. This one's tetrahedral molecular geometry. That's methane. So C is the answer. Okay, let's see what we got coming. 51. Let me scroll that. Maybe we just got 53. Yeah. Okay, select the correct number of atoms in one molecule of dichlorine monoxide. Dichlorine monoxide. Number of atoms. Well, 3, obviously. Type 3 compound. We just said how many there were. Non-metal, non-metal. 2, 3. That's too easy. How about 53? Select the correct number of atoms in one molecule of hydrazine. Ooh, hydrazine. What is hydrazine? We didn't talk about that in class, did we? Hydrazine is, well, let's see. It's not used too much anymore in rockets, but it was for a while. It's extremely hazardous. The Germans during World War II were experimenting with it in one of their little rocket plane. I forget what it's called. I don't remember what his number was. It was Messerschmitt. But they had hydrazine and some other compound that they combined, and they instantly reacted. In other words, you didn't need ignition source. They were very hazardous to work with. Hydrazine is that as your foundation, and then hydrogens. There you go. N2H4 is hydrazine. So, correct number of atoms, 1, 2, 3, 4, 5, 6. 6 atoms. Okay. I can't remember what they reacted with. But the technical term for it is hypergolic. When you put two chemicals together and they immediately exothermically react, they're called hypergolic. We still use hypergolic compounds, reactions in attitude control jets on our spacecraft because we don't need a lot of the stuff. We don't have to carry a lot of it up there, so it reduces the hazard. Plus, we don't have to ignite them to make them work. Not like you do with the main engines of, say, the space shuttle, where you had hydrogen and oxygen coming together. And you can see, if you go back and look at videos of those rockets right before they take off, there are sparks being thrown into the space underneath the rocket engines. They throw those sparks in, and then when they combine the hydrogen and oxygen, the spark sets them off. And once they get going, they're self-perpetuating. But the hypergolics, you just put them together and they react. So the control jets are small, right? So you don't have to put a lot together, so that reduces the hazard also. Let's see. Now let's scroll down to. Can I get on there? I can get 3 on there. Good. 55. The formula mass of ammonium phosphite, NH4 3PO3. What's the formula mass of ammonium phosphate. Okay, I need my calculator for this one. How many nitrogens do you have? 3. So we need 3 times 14.01 for the nitrogens. And we have 12 hydrogens. We have 1 phosphorus, which is 30.97. And we have 3 oxygens. Rounded off to 2 decimal places. So we just have to say, all right, I'm going to start from the bottom and work up 48, 30.97, 12.12 for the hydrogens, and 3 times 14.01, add that in there. I get 133.12. Close enough. Pick the best answer. I think that's a rounding error. They probably rounded these guys off. They definitely rounded this one off. Let's see, if I'm 1, 2, and they're 9, that would be a difference of 0.03. Maybe. That one might be rounded also. Okay, 56. Which of the following statements concerning Avogadro's number is correct? Is correct. Has a value of dead batteries. Pause for a battery exchange. Let's see here. Batteries. Got batteries. Oh, I got extra batteries in here somewhere. Ooh, wrong size. Wrong size again. Tell me I didn't bring any with me. Ah, here we go. Oh, the Boy Scout for 6 months. Always prepared. I had to quit to make money. Got paper route then. Back then, paper routes were the going thing. Could make a little money. At one time, I was up to 150 papers a day on a bicycle. That was a tall order. There we go. It's working. Let's see. All right. Which one is correct about Avogadro's number? 6.02 times 10 to the, oops, wrong sign. It's not minus 23, it's plus 23. Okay, it denotes the number of molecules in 1 mole of any molecular substance. Yep, that's true. Right. It is the mass in grams of 1 mole. No, it's not mass, it's numbers of stuff. It denotes the number of atoms in 1 mole of any substance. Not necessarily. If you have a mole of water molecules, you'll actually have 3 moles of atoms. Right? So D is false also. D is tricky. You know, if you don't stop and say, whoa, wait a minute, what is that saying? Then it turns out that B is the only answer that's correct out of that one. 57. Avogadro's number of sulfur atoms would have a mass of what? Well, it's obviously not going to be this. That's way too big and that's way too small. That's oxygen. It has to be 32. It's sulfur. 32 grams of sulfur atoms would be 6.022 times 10 to the 23rd of them. All right. Let's see. Scroll. Oops. We'll scroll again when we get to 59. 58. Okay. Which of the following samples has the largest mass in grams? The largest mass in grams. Okay. We're going to have to do Henry Ford. Okay, so for carbon dioxide, we've got 12.01 plus 2 times 16. Right, I'll do the calculation in a minute. Oh, times 5. Times 5. And CN is 12.01 plus nitrogen, 1401. Right, times 6. And then water is, I know what that one is, 18.02 times 7. And then hydrogen is 8 times 2.02. 2 times 1.01. So, which one has the largest mass? Well, let's see. 32 plus 1201. 32 times 5 is 220. 220.1. 220. That's probably going to be close enough. Grams. This one is 12.01 and 14 times 6. 156. Okay. A is still high. 7 times 18.02. 126. And 8 times, well, we know that's not going to be big enough. Right? So A wins. 59. Let's scroll that a little bit. Yeah, there we go. And which of the following is the correct setup for the problem? How many atoms are present in 10.4 grams of germanium? Where are we starting and where are we headed? How many atoms? 10.4 grams of germanium is where we're starting. 10.4 grams. This is a dimensional analysis. Right? We're converting from one unit to another. Grams of germanium to atoms of germanium. So we need to get rid of the grams and make moles first. Right? So germanium, I don't have that memorized. 7259. And then we need to change moles to atoms. Right, so we need Avogadro's number. There we go. Now, the way they've got it set up, it may not be linear like this. So we look, which ones start with 10.4 grams? They all do. Then, which ones have 1 mole divided by 72.59 grams? 1 mole divided by 72.59 grams. Yep, that one does. That one does. That one doesn't. So it's either B or C. And then the third part is Avogadro's number on top. Atom moles. No, that's not right. That's wrong. That's wrong. Yeah, it should be atoms and mole, right? Because this cancels that mole. That gram cancels that gram, leaves you with atoms. So none of them are right. Okay. Number 59 needs some doctrine. 59, this needs to be. Yep. What's that? Okay. All right, moving on. 61. Which set of coefficients balances the equation? C4H10 plus O2 yields CO2 plus H2O. Still on the board? Yeah. Video. Okay. We probably ought to set up, this is a hydrocarbon. And if I didn't tell you already, whenever you burn a hydrocarbon in oxygen and you make carbon dioxide and water, you're always going to have to use the fraction trick at the end, except for methane. That's the only one that you don't. But for the rest of them, you do. So let's set up a budget. We got carbons, hydrogens, and oxygens. 4 carbons, 10 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay, I start with carbon. 4 carbons. So that makes 8 plus 1 is 9 oxygens. Okay, now hydrogens, because we're saving the oxygen till last. So hydrogens, we need 10 hydrogens on this side. So we need 5 here. That gives us 10 hydrogens. 5 plus 8 is 13. Okay. Now we need 13 oxygens on this side. There we go. Now we need to get rid of that fraction. So if we multiply the whole thing through by 2, that'll get rid of this here. That'll put a 2 there, 8 here, and a 10 there. So it's 2, 13, 8, and 10. 2, 13, 8, 10. Okay? All right, 62. Potassium forms an oxide with the formula K2O. Okay, I'll buy that. What's the coefficient of oxygen in the balanced equation for the reaction potassium with oxygen to form the oxide? So we got potassium together with oxygen, right? You got to be sure and write that correctly. It's one of those diatomics. K2O, and that's a solid also. Okay, we probably won't need the budget for this one. You need 2 potassiums over here. Oops. Let's start with oxygen. You need 2 oxygens over here. Now we've got 4 potassiums. There we go. 2 oxygens, 4 potassiums. We're good. Okay, the coefficient of oxygen is 1. Okay, we didn't change it at all. And this is a synthesis reaction. Oh, another one. Let's see if this one's wrong. 64. Which of the following is the correct setup for how many grams of water will be produced from 2.1 moles of oxygen in excess of H2S according to the reaction? Oh, this is a stoichiometry problem. Okay, so they're giving us the balanced equation. That's nice. And 2 waters and 2 sulfur dioxide. Okay, yeah, it's still showing. Okay, what are we given? 2.1 moles of oxygen. 2.1 moles of oxygen and an excess of H2S. So we're going to convert all of that into water. So we want to know grams of water. Okay? Remember, in a balanced equation, you can't go anywhere unless you got moles. Right? We've already got moles right here. So we need to convert that many moles of oxygen into moles of water. And the conversion factor is the ratio of coefficients. 2 waters, 3 oxygens. So 2/3 of that value would be 1.4 moles of water, right? 3 into 2.1 is 0.7 times 2 is 1.4. That's how I did that. Then we need to convert this. Well, let's do it this way. Be consistent. That times moles on the bottom, grams on the top. If I want to multiply that, I need this one in the numerator to cancel that one in the denominator. And the conversion factor is the molar mass of water. So 18.02 times 1.4. And I get 25.23. 25. Oh, they just said set it up. Okay. Let's see. 2.1 moles of oxygen. All right. Those are all correct. Then we're going to convert here. 2 waters on top, 3 oxygens on the bottom. That's right. Here. That's the only one that's right. So it has to be this one. And then let's check that part. 18 on top, 1 mole on the bottom. Okay. Cover that up. This times that. Okay. Okay, 65. Good on time. Half hour. The atomic masses of helium and beryllium are 4 and 9.01 respectively. Atomic mass units. So that's how much each atom weighs. Helium's 4, beryllium's 901. Which of the following statements are true? A mole of beryllium contains more atoms than a mole of helium. Which one contains the most atoms? Which of the following? Atomic mass. Well, if you've got the same mass, then you would have more atoms than helium. But a mole of beryllium contains more atoms than a mole of, that's kind of stupid. Right? A mole is a mole. They're the same. A mole of helium is heavier than the mole of beryllium. Now that's a valid question, but still wrong. A mole of beryllium would weigh more than a mole of helium because each atom weighs more. So B is wrong also. A mole of beryllium contains the same number of atoms as a mole of helium. There you go. That's it. C is the answer. 70. Let me scroll it up a little bit. There we go. So, true or false? 2 moles of NO contains the same number of oxygen atoms as 1 mole of CO2. 70. 2 moles of NO, okay? We have 2 moles of that. How many moles of oxygen do we have? Moles of oxygen atoms. Same number of atoms, we have 2 moles of oxygen. Because 1 to 1. For every one of these, you have 1 oxygen. So if you have 2 of those, you have 2 oxygens. Oxygen atoms in CO2. CO2. 1 mole of this, for every one of these, you have 2 of those. So 2 times 1 is 2. That's true. This one's correct. The coefficients in a balanced equation give the fixed molar ratios between reactants and products. That's true. Once it's balanced, those coefficients give you the mole ratios of each of the reactants and products. So 2 is true. Avogadro's number is experimentally determined quantity. That is true. That's just a statement of fact. So they're all true. If I didn't mention that during the lecture, maybe that's why I put this one in here. So be sure to get that fact on record. So they're all true. 75. Contrast the magnitudes to 3 significant figures of Roman number 1, moles in 28 grams of nitrogen, moles in 28 grams of carbon monoxide, and then select an appropriate response. 1 is greater than 2, 1 is equal to 2, 1 is less than 2. Okay, so the moles in 28 grams of nitrogen. If we have 28 grams of dinitrogen, that's 1 mole of molecules. Because each nitrogen is 14, 28 grams would be the molar mass for that molecule. So this is 1 mole of nitrogen. How about carbon monoxide? Carbon monoxide. 28 grams? 28 grams. So carbon is 12.01, oxygen 16. Close enough. Actually, this one would be 28.02. But if we're rounding off to 1 decimal place, then yeah, they would be equal. Just chop this off, chop that off. So 28 grams of each is the same number of moles of each one. So that's why B is the answer. 1 is equal to 2. Let's see here. 76 trombones. Go. 76. Contrast the magnitudes to 3. Wait a minute. Oh, okay. 3 significant figures. All right. I second guessed myself. 3 significant figures. Here we go. Molecules of 28 grams of nitrogen and 28 grams of oxygen. Well, nitrogen that's 1 mole. 28 grams of oxygen, since it's 32, that's less than a mole. So you would have this one is greater than that one. Okay. $77. Select the set of coefficients from the response list that correctly balances this equation. So, oh, okay. So methane is going to give us propane plus hydrogen. It's probably how they make propane. Okay, so coefficients. Since we have hydrogen in two different places, we better use the budget. Carbon, hydrogen. So 1 carbon, 4 hydrogens, 3 carbons, and 10 hydrogens. Carbons, we need 3 here. That gives you 12 hydrogens. And on this one, we need, let's see, we got 8 here. We need 4 more. Okay. That should be it. So it's 3, 1, and 2. 3, 1, and 2. Okay. When you've got an element split between 2 compounds or a compound and an element, so it's easy to, when you start to manipulate the coefficients to balance it, it's easy to put blinders on and not see that other source. You have to actively look for all of that element in that side of the equation. I do that all the time. I have to be careful. 79. Using the balanced equation for this combustion of ethane, right? How many molecules of oxygen that react? How many molecules of oxygen react with 2 molecules? That doesn't need to be there. React with 2 molecules of C2H6. Well, 2 molecules here means that 7 molecules of oxygen. There's no calculating to be done there. Just read the coefficients. Even though the prose is wrong. Grammatical errors. Let's see. Okay, we'll do this one. What is the molecular geometry of H2S? 81. H2S. So we got 2 electrons here, valence electrons. Sulfur is oxygen group at 6. So we have 8 electrons. We have sulfur, hydrogen, 2, 4. Means we have 4 left over. Can't put any more around hydrogen, so we have 1, 2, 3, 4. Okay? Molecular geometry. Well, the electronic geometry is 1, 2, 3, 4 is tetrahedral. But if we put it in a tetrahedron, like that, and we put sulfur in the middle, we put lone pairs here, hydrogen in the back, and hydrogen here, then the bonds between these two, that was a poor choice. I should have put it over here. Let's do that. With the lone pair in the back, hydrogen over here. Now the bond between hydrogen and sulfur is bent. I think your textbook may use angular. Yeah, I like bent better. Oh, which makes it B is the answer. Oh, is that it? That's it.